From the previous video, we have discussed series and parallel circuits and have defined Kirchhoff's current law and Kirchhoff's voltage law, as well as the voltage divider and current divider. In this video, we will be using these to solve complex circuits. But what is a complex circuit? A complex circuit is a combination of components that are neither series nor parallel. It can be a combination of a series and parallel circuit, or it can in combination with a Y-connected components or with a delta. A complex circuit can be solved by different network theorems, one of which is Kirchhoff's voltage law and Kirchhoff's current law, or through as simple as applying characteristics of a parallel combination and series combination. But before we proceed, let us first define what is a node and what is a loop. A node is any point in a circuit that connects two or more circuit elements. In the figures, point A, B and C are nodes. In a circuit analysis, nodes can be used to simplify a circuit. Referring to figure 2, to simplify the circuit's nodes band C were shown into a single node. This method of simplifying circuits by combining similar nodes is called nodal analysis. In the given circuit we have defined nodes A, B and C. Also we have defined current I1 which is equal to 5 amperes, I2, I3, I4 which is equal to 10 amperes and I5. From the given circuit we will be doing a KCL, which is defined as the algebraic sum of currents leaving and entering a node to be equal to 0. We will first do KCL in node A, assuming currents entering to be positive and currents leaving to be negative. By applying KCL to node we obtain I2 minus I5 to be equal to -5, and applying KCL at node B we obtain I2 plus I3 to be equal to 5, and by applying KCL to node C we obtain I3 plus I5 to be equal to 10. A loop is a closed path formed by starting at a node, passing through a set of nodes, and returning to the starting node without passing through any node more than once. In the given circuit we have defined A, B and C as a loop. This circuit contains 3 loops, however we have only defined one because we cannot conduct Kirchhoff's voltage law in a loop containing a current source. But to begin, it is important for us to know that the conventional assumed flow of current, used in circuit analysis, is that the current flow from the positive polarity to the negative polarity. Now let us conduct KVL in this circuit. To begin, let us define that we will be using the element's polarity as the entry of the loop. Conducting KVL in the loop we obtain the equation to be 4 of I2 minus 2 of I3 plus 6 of I5 to be equal to 0. By using KCL and KVL in this circuit we have formulated 4 equations that will be used to solve the circuit. To solve the circuit we will be using equations 1, 2, and 3. The 4th equation will be used for checking. Why can't we use equation 3 for checking? We cannot use equation 3 for checking because this equation contains the resistance value of each element, thus makes it important in solving the circuit. Now let us solve the equation. To do this I will be using my Casio scientific calculator under equation mode. After solving the result we obtained I2 to be -5 amperes, I3 to be 10 amperes, and I5 to be 0 amperes. From the result I2 to be -5 amperes, this denotes that the assumed current direction is opposite to the actual current. In the given circuit we will not be solving this by applying KCL or KVL but through formulas from series and parallel circuit. In this approach we will be doing the breakdown and simplify the approach, meaning we will slowly simplify the circuit into one resistor, and once we have computed the total current supplied by the source we will slowly rebuild the circuit. To begin we have defined sections in the circuit which are sections A and B. In the section we can see resistor 1 and resistor 2 to be connected in parallel, and in section B we can see resistor 3 and resistor 4 to be connected in parallel. Now to simplify sections A and B, we will be using formulas from a parallel combination. This will give us to be the equivalent resistance of section A as 71.43 ohms and the equivalent resistance of section B is 127.27 ohms. Now we have simplified the circuit as a series combination of RA and RB. To further simplify the circuit we will be using the formula from a series combination, which is the equivalent resistance to be the sum of the resistors connected in series. Now we have simplified the circuit into one resistor only. This equivalent circuit means that no matter how complex the circuit, the voltage source only sees the equivalent resistor as its load. Now that we have simplified the circuit, we can now compute for the total current supplied by the source. By applying Ohm's law, we can solve the total current to be 0.12 ampere. Now let us rebuild the circuit. Now we will be rebuilding the circuit for us to solve the individual currents and individual voltage drops. For the sake of discussion, we will try to approach this in such a way that we will be using the voltage divider formula and the current divider formula. In this simplified circuit we can use the voltage divider formula to solve for the voltage drop at RA, which will be equal to the voltage drop at R1 and R2. And also solve for the voltage drop at RB, which will be equal to the voltage drop at R3 and R4. We have also tried to compute for the individual voltage drop using ohms, from which we can notice a slight difference in results, which is probably due to the rounding of digits. In the rebuilt circuit we can now solve for the individual current using the current divider formula. Notice that the total current will be the current that will be shared by the combination of R1 and R2, and as well as the combination of R3 and R4. Using the current divider we have obtained I1 to be 0.085 ampere, I2 to be 0.034 ampere, I3 to be 0.044 ampere and I4 to be 0.076 ampere. I hope you have learned something from this video. For comments and suggestion, you may also email us at ingnotebook966@gmail.com.